So today in the third lecture of the series on galaxies, we look at the properties of the groups and clusters of galaxies. We looked at this in the first lecture where we said galaxies live in all kinds of systems. There are elliptical galaxies, there are spiral galaxies, and they are normally found in small groups such as this, or in very rich clusters where there can be up to thousands of galaxies. And together the galaxies are much more than just a simple sum of their parts. We will look at some of these properties today. We also said that we live in one of these groups. We called it the local group, where our galaxy, that is the Milky Way, which is out there, and the Andromeda galaxy, along with various satellites, sit in a group of two large galaxies and many smaller galaxies. We know of about 70 or 80 galaxies in all that form the local group, but there are only two major galaxies in there. In the general scheme of things, all these groups are part of a very large scale structure, a filamentary structure, which describes the universe. We call it the cosmic web. As you can see, this is a dark matter simulation that shows the distribution of matter in the universe over hundreds of megaparsecs. If we take a system like this, and here we are looking at just the underlying dark matter in the system, we can see that we can call one of these systems, say, a cluster, which has many hundreds of galaxies, and something much smaller which has a few galaxies, maybe a group. And all this entire network is full of groups and clusters distributed on this filamentary structure. As we go from galaxies to groups to clusters, the properties of these systems behave in a self-similar manner. For example, as you can see, I have tabulated here how the values of their luminosities in the X-rays, for example, or the temperature of the gas that is in between the galaxies, or the mass of the baryonic component of the cluster, etc. They all scale as we go from the smallest system, the galaxies, to groups, to clusters, and we will come back to the various large scale properties a little later. We find that most of the galaxies in the universe live in very small groups, like our own local group. Very few live in large clusters. It is easier to study clusters because a large number of galaxies are there in a small volume, but most galaxies do not live in clusters, and this is why it is very important to study small groups. They are difficult to do, and it is a subject that is only picking up now, the study of small groups. This plot shows this in a very succinct way. This is taken from the 2DF redshift survey, and you can see this tells you the fraction of galaxies that are in groups that have mass or light in logarithmic units, 10 to the power 10, 10 to the 11, etc. So, for example, this shows, the x-axis here shows the light in 10 to the power 12 solar luminosities. That is a typical luminosity of a cluster, and you can see only maybe 5% of all galaxies live in such systems, whereas our local group is of the order of 10 to the power 10.5 or 10 to the power 10, something like that, and you can see most of the galaxies live in such groups. What are groups and clusters made of? They are made up of galaxies, and in these galaxies there are stars. So these are baryonic, which means that they are made up of quarks like you and me. Then there are intergalactic stars in between the galaxies. Then in between the galaxies, in the cluster or group, there is gas, which can be hot, which is X-ray emitting, as well as cold, which can be detected by radio telescopes. And there is dark matter that is holding together the entire cluster or the group, and this is non-baryonic. So we are going to look at all these different components one by one. In looking at the constituents of clusters, let's look at what the clusters are predominantly made of. The light comes from the baryonic component in the cluster, and these come from the stars within the galaxies. If we look at the optical image of a cluster, you can see lots and lots of galaxies in it. Now these galaxies have stars, and these represent the main baryonic component of the cluster, the stars within the galaxies themselves. Now actually, if you look at the total matter in the cluster, the amount of matter is much more than what you see in the stars, but an observational astronomer looks at the optical light from the galaxies and infers the various physical properties of the cluster. If you look at the total number of baryons in the cluster, we can estimate the total number of baryons in the universe, and the baryon fraction turns out from the latest measurements from the Planck satellite of the cosmic microwave background to be about 17% or so. But looking at the stars in a cluster, it is almost 0.3% of the total matter in the cluster. So there are other types of baryons that we don't see through light. In fact, as we will see in the next few slides, there is neutral gas, which is the cold gas, atomic gas in the cluster that also contributes to the baryonic component of the cluster. Then there's molecular gas, and then there's the hot gas, which is emitting X-rays, that also contributes to the baryonic component. But if we add all that together, there is still quite a lot of baryons that are unaccounted for, and this is one of the unsolved problems in modern astrophysics. Where are the missing baryons? One clue comes from looking at very deep images of clusters. Here is one of the deepest optical images ever taken of any cluster, of the Virgo cluster, which is our nearest cluster. And you can see that these galaxies, which are marked in red, are often seen as what you see here in the red, only that big. But as these images have been built up by images taken by the same telescope over almost a decade, 10 years, and added together, one can see very deep images of the same cluster where we are beating down the sky background and looking at faint objects. And as a result, you can see these streams of stars that connect the galaxies within the cluster. You can see there are a lot of stars in between the galaxies. And these are stars that are lost from one galaxy or maybe torn away from one galaxy by interaction from another. These are the intergalactic stars. People are trying to figure out whether if you add the total amount of mass of the intergalactic stars, will they add up to the total number of missing baryons? This is still unsolved. We get a hint that this won't be enough, and we might have to look at other forms of gas, maybe cold gas or hot gas, that we have not detected yet. The other forms of gas in between the galaxies that we can see is in the form of neutral hydrogen, which gives an indication of the atomic gas in galaxies. This picture shows in negative, black on white, the optical part of a spiral galaxy, but you can see that the contours represent the atomic hydrogen that has been observed by a radio telescope, and you can see that this is much more widespread than the stars in a galaxy. This forms part of the atomic hydrogen component, the cold gas in a cluster. You can see that if you look at a group in which there are some galaxies that you can see in an optical image, if you move over and look at what's happening in the radio image, you can see there's a lot of gas that you can see in between the galaxies as a product of the interaction between the galaxies. So there is a lot of cold gas that is also seen in the group or the cluster in between the galaxies. And then we can see the hot gas in a cluster, and here are images from the Chandra satellite, where the colored part, the purple or the orange part, these are all show the hot gas, the 10 million degree hot gas that is the intergalactic medium that exists in between the galaxies in the cluster. And this has become so hot because of the very deep gravitational potential due to the dark matter in the cluster. But this is the baryonic component that shows us that there is more matter than just the baryonic component of the clusters. If we look at what the clusters are made of, almost 90% of the mass of the cluster is made up of dark matter. How do we know this? We can do many kinds of observations to find out the presence of dark matter, because dark matter gravitates. We can sense the gravitational force of the dark matter, and this dark matter holds the cluster or group together. One way of doing this is to use a dynamical method called the virial theorem. Now, in the virial theorem, which you must have come across, what we find is that if you have a system in equilibrium, and in this equation you can see in this equation on the right hand side in the virial theorem, T is the total time averaged kinetic energy of the dynamical system, and the dynamical system would be all the galaxies, and the dynamical system would be all the galaxies and all the dark matter, everything all together. The total kinetic energy, twice the total kinetic energy, plus the total potential energy of the entire system, again averaged over time. When we add the two together, you come to the left hand side, and in equilibrium this will be 0. So twice the kinetic energy plus the potential energy will be 0. And if we assume that a cluster is in equilibrium, we can, through measuring these, try to find out the total mass of the cluster, irrespective of whether it emits light or not, and thus we can measure the amount of dark matter in the system. So here is my virial theorem again, 2T plus V equals 0. The total amount of potential energy of a spherical system, let's assume the cluster to be spherical, the total amount of potential energy of this spherical system can be calculated very simply by assuming that the cluster is made up of shells, and each of these shells, which have a volume of 4 pi r squared dr, density, uniform density rho as a function of r. Each shell is very thin, and within each shell the density is the same, which is rho as a function of r. Then the mass would be 4 pi r squared rho r dr, and you assume that this shell is brought from infinity to where it is now in this particular spherical system, and the energy that you need to bring it to this system is the potential energy that is stored in the system. So if you integrate over the entire radius of this system, it is a very simple integration to do, and the answer you get is minus 3/5 gm squared over r, where m is the mass of the cluster, the total mass, r is the radius that can be measured, and the gravitational potential energy is negative because you've had to expend energy to bring the whole system together. In 1933, Fritz Zwicky, who was a visionary astronomer, used this argument to try and estimate the mass of the Coma cluster, which is one of our nearest clusters of galaxies, and found that the total amount of matter that he was estimating was far more than the amount of matter that you see in the galaxies. So we've estimated the potential energy. How do you estimate the kinetic energy? What you do is you have redshift or radial velocity measurements of lots and lots of galaxies in the cluster. You take the velocity dispersion, the dispersion of all these velocities, because the average of all these velocities will be the average velocity of recession from the Earth. So you need the velocity dispersion, and that dispersion, because it is calculated from just the radial component of each velocity, you have to multiply it by 3 to get the radial velocity of the three-dimensional velocity dispersion. Once you do that, you add the two together and you get t times 2 plus v, which is the minus 3/5 gm squared over r. These two put together will give you the mass of the cluster, because you can measure the radius of the cluster from observations. In order to do this, what you have to do is you have to look at the velocity distribution of a cluster, and one of the major things you have to do in order to calculate the velocity dispersion is to trim the outliers, because if you keep the outliers, which might be background galaxies, or in this case foreground galaxies, then that adds to the velocity dispersion. This is a practical thing that you have to do, and once you've done that, then you come at a very sensible mass of the cluster, and this is what Zwicky found. Zwicky found that from the virial theorem, the mass you get is way over 10 to the power 15 times the mass of the Sun, whereas if you take the masses of the galaxies that you assume from the measured light of the galaxies, that is at least a factor of 10, if not more, less than the mass that you're getting from the virial theorem. He called this unseen matter or dark matter, and of course in the 1930s nobody believed such a thing existed. It was only when dark matter was measured from the rotational curves of spiral galaxies in the 1960s that people started to take this kind of calculation seriously. Once we know that the clusters or groups are predominantly made up of dark matter, we can try and see whether we can find or measure the presence of dark matter through various means, because if we do that with just one method like the dynamics, there might be some assumptions that are inherent in it that might affect our conclusions. If we do it by independent observations, then it does not matter what kind of assumptions we make when we make a certain calculation. Here I'm going to talk about two different ways of measuring the amount of dark matter in systems like groups and clusters. In each of these pictures, which are taken from 3 different sources, one of them is the Hubble Space Telescope image of the cluster, and there on the dark background you see white images of galaxies. The tiny little things that you see in the galaxy are the galaxies, and they are from the Hubble Space Telescope images. These are the optical images of the clusters. On top of it are superposed in red the X-ray image of the cluster, which comes from the Chandra X-ray satellite in space, and this gives you the hot gas, the 10 to the power 7 degree hot gas that is in between the galaxies in the cluster. And also you get in blue the presence of the dark matter of the cluster, which is inferred through a method called gravitational lensing, which I'm going to talk about a little later. So you can see the dark matter, the hot gas, and the baryonic light matter, the stars, in the same picture. And you can see that in general the cluster is filled with all of these things, but sometimes they are not in the same place. So one has to study all of these components to make sure how the cluster is made up, and sometimes they are displaced from each other because clusters are interacting with each other, and 2 or 3 clusters might have merged just like galaxies merge. If you look at the same pictures, you can now see separately the X-ray emitting intergalactic medium, and you can see how different they can be in between clusters. And then in the next image you can see the dark matter separately, so that you can see how they are related to the underlying galaxy population, because the optical images are also in the same plots. And in the next image we are bringing them all together again, like in the first image, to see all the 3 pictures together. Okay. Now let's concentrate only on the X-ray image. Now here are 2 images. On the left, we have an optical image of a cluster called Abell 3528. And you can see all these little tiny white specks are actual galaxies. This is a very deep optical image of this nearby cluster. And on the right, you see an X-ray image from the ROSAT satellite, which is a German satellite that flew in the 1990s. And here you see in color, the false color, the X-ray image of the same cluster, where the color coding goes from red, which is the hottest, to yellow, which is the cooler part of the cluster. You can see in the center it is white, which is the hottest, and then red, and then yellow. And this shows how, unless you see what's going on in a cluster, you can't figure out what the constituents of the cluster are, because the hot gas in the cluster maps the dark matter distribution. And just from the galaxies are the same. That's the big galaxy in there, and there's another big galaxy in there, right? And the same two big galaxies are shown in the two clusters here and here. And the underlying X-ray gas shows that actually there are two clusters in here that are interacting with each other. They're about to merge. They're coming together. The X-rays from the hot gas, since it actually maps out the underlying dark matter, helps us understand how much dark matter there is and where the dark matter is. And you can use it to measure the amount of dark matter. So to do that, to use X-rays to find the mass of the cluster, one has to, just like the virial theorem argument, assume spherical symmetry. We can do that, for example, in a cluster like 3528. We can do it for the two different clusters separately. We can assume them to be two spheres. And then we also have to assume some kind of a hydrostatic equilibrium, and that is given by this equation, which comes from the pressure gradient of the cluster, and it shows the difference, the relation between the pressure gradient of the cluster and the distribution of matter in this particular system. We also use the ideal gas law, the perfect gas law, and if you put the two together, then in the next one you can see we can put the two together, assuming some kind of a abundance distribution of materials in the cluster. The equations come together to give you a relation between mass as a function of radius in the cluster and the gradient of its density given by rho, d log rho dr, and the gradient of the temperature, d log rho d log t dr, and various other fundamental constants like the mass of the proton, the Boltzmann constant, etc. And there's a temperature term there as well. So if one can measure the distribution of density in a cluster from, say, the X-ray profile of a cluster and the temperature profile of the cluster by fitting models to do with thermal Bremsstrahlung that causes the X-rays from the cluster, one can measure these two, one can measure the mass profile of the cluster. So the X-ray observation of the cluster can give me an independent measure which doesn't depend on the virial theorem. It can give me an independent measure of the mass of the cluster. And so you take pictures like this, for example, this is again pictures of the coma cluster. Here is an X-ray on the right, X-ray image of the coma cluster put together with an optical image, and from this one can break this up into shells and find the X-ray luminosity of the cluster as a function of radius, as well as measure the temperature as a function of radius, and get the same answer, which is the total mass of the coma cluster from X-rays, which you get from the virial theorem. This gives us some assurance that we are measuring the same thing. The assumptions of the two systems are different. Apart from spherical symmetry, the virial theorem does not assume the same principles as the ones that we did in the X-ray masses. There is a more direct way of measuring the mass of the cluster without any of these assumptions, and that is to do with the bending of light. So here is a phenomenon called gravitational lensing, where what happens is a direct prediction of Einstein's theory of relativity, and that is, as we know, that if there is gravitating matter anywhere, it locally distorts space-time, and as a result, as a beam of light is traveling across the universe, it goes along the contour of space-time. When it passes massive objects, it bends. So here we are observing from here, we are observing from here, and we are observing a cluster of galaxies, which is here. But actually what we are also observing in the same image are distant galaxies that are behind the cluster. So as the ray of light passes or comes through the cluster of galaxies, which has its dark matter halo and the galaxies in between, and comes to us, we can see the light as it has come through this whole system, but it is actually bent as it's come to us. But we don't see the bent ray, we think that the light has come from there, and so we see multiple images of the same background galaxy in different places. Not only do we do that, we see them as distorted. This is known as gravitational lensing. The light that comes from distant galaxies feel the presence of the matter it passes or comes through, and so we can map out the dark matter that is in the cluster through the distortions of these galaxy images. You can see that here are images of galaxies that are almost complete circles, and this is what happens when there is a background galaxy that is completely aligned with one of these lenses, which is a cluster, and so the light that is coming from background can come from all different angles to us and then appears to us as a ring. And this is known as an Einstein ring because it was predicted by Einstein's general theory of relativity. And these are two of the many examples of the Einstein rings that we have detected, in which we can see a galaxy as a complete circle. Now, if the galaxies are slightly misaligned with the axis of the lens, then you won't see the full ring, but you will see a galaxy as distorted arcs, which are parts of the ring. And this you can see in very deep images taken by the Hubble Space Telescope. Here are details of the Hubble Space Telescope, very high resolution images of a cluster called Abell 1689, and you can see so many of these distorted arcs, and in many cases they are arc-like images of the same galaxy that we see in multiple places spread around a whole circle. So these are parts of the Einstein ring that come from the same galaxy. In this particular image of Abell 2218, there are images of at least 100 distorted galaxies that are in the background. Remember, we are looking at galaxies in the cluster, the ones that are yellow and red. These are the galaxies in the cluster. The blue galaxies are the ones that are in the background, from which light is coming to us through the cluster, and so it is being bent, and we see these images as distorted. That helps us infer the mass of the cluster. We can do a very detailed modeling of the mass inside the cluster of the galaxies by looking at the distortion of the galaxies that are imaged in this way, the lensed galaxies. This is a matter of ongoing research. A lot of groups across the world are now looking at how to model the mass inside a cluster by looking at the distortion of all the galaxies that you see inside and on the periphery of this cluster. This gives us a direct way of measuring the mass of a cluster, the dark matter content of the cluster, because this does not feel only the galaxies from which you see the light, but also the matter, the total matter in between the galaxies. This gravitational lensing can be done both from just by modeling the arcs, which is called strong lensing, or by modeling in a statistical way the distortion of all the galaxies that you see around the cluster. This is known as weak lensing, and this is a good way of finding out directly the mass of the cluster. Here, no assumption is being made about spherical symmetry or virial equilibrium or anything of that sort. The only way this is done is purely geometric. It uses Fermat's principle, which is and some equations from Einstein's general theory of relativity. And so this is a most direct way of measuring a clumpy system which can be largely aspherical. So we're putting everything together. We can see that in general the mass estimates that you can see from gravitational lensing and from X-rays give you roughly the same result, telling you that the mass to light ratios of these cluster systems are close to of the order of 100, which means there is 100 times more, up to 100 times more dark matter in these systems than there is matter in the galaxies. Sometimes in systems like the Bullet cluster, which is very famous now, and there are many other systems that are now being uncovered like it, we see that the dark matter, here shown in blue, and the red part, which is the hot gas, they are displaced from one another. And this has happened because the two clusters have collided with each other and are causing this. And so this is a good example of clusters that are not in equilibrium, but still you can actually measure the mass of a cluster like this through gravitational lensing. This is a very rich subject of research right now, as more and more of these systems of galaxies, groups and clusters are being studied in all its components, the X-rays, the light component, and also the dark matter.